doubt, then you can ask me from the last classes, because we will go to the next level of the final level of tools of quantum mechanics. So before that, if you have any genuine doubt, and then we can talk little bit. Okay, so I think I must start. Am I audible to you?
Yes, sir.
Okay. So in the last class, we have learned what are the operators, and we have also give the definition of what is eigenvalues and eigenvectors. And we need the eigenvectors corresponding to eigenvalue such that they can make a complete basis. Obviously, you can have n number of eigenvectors, but what is important, that vectors belongs to Hilbert space and they can form a complete basis. So what I want to tell you, I will just give you one example, and let's try to understand all this thing with the example. And you can find that when eigenvalues are non-degenerate, there is not any problem. But the real problem occur for the eigenvectors corresponds to degenerate eigenvalues. And it's a really huge problem into the quantum mechanics at the practical level. And so why we need to degeneracy have to be broken. And then we can insert the perturbation and all kind of thing into our calculation into for as a tool to analyze the system. Anyway, we will discuss it at time of perturbation, but today first I am going to explain all about eigenvalues and eigenvector with an example, and why degenerate eigenvectors are real problem. And then we will go for the final stage of a commutator algebra and what is commutators in a quantum mechanics. So let's try to go for the eigenvalue and eigenvectors. So suppose I have one beautiful operator, and let's say this operator is 1 0 0 0 0 1 0 1 0. So this is the operator. What I have to do, I have to find the eigenvalues and eigenvectors of this operator. So what I have to do, I have to solve the secular equation. And once I will solve the secular equation, 1 minus lambda 0 0 0 minus lambda 1 0 1 minus lambda, that must be equal to 0. And what you have 1 minus lambda, and lambda square minus 1 must be equal to 0. So what should be the lambda? So lambda 1 is equal to, let's say, minus 1. Lambda 2 is equal to 1. Lambda 3 is equal to also 1. So what we have, this is non-degenerate and these two are degenerate. So obviously, let's go for the finding the eigenvectors for non-degenerate eigenvalue, that is lambda 1 is equal to minus 1. And obviously, we will always try to find orthonormal vectors because I just wanted to use it as a unit vector. Something like I, j, k as a unit vector as well as basis vector. So we will just use all this concept. So let's say for lambda 1 is equal to minus 1. Let's say phi 1 is identified as a1, b1, c1, or you can write anything. A1, b1, c1 is good number. So what we will do, we have to follow this particular thing 1 0 0 0 0 1 0 1 0, and this will be a1, b1, c1 must be equal to minus 1, and that will be a1, b1, c1. So what will be the equation? The equation is a1 is equal to minus a1 and c1 is equal to minus b1 and b1 is equal to minus c1. So these two are same thing. These two are same thing. What is meaning of a1 is equal to minus a1? Meaning of a1 is equal to minus a1 is equal to a1 must be equal to 0. And how many solutions you have? b1 is equal to minus c1. You have infinite number of solutions. So what should be the form of kit phi 1? The phi 1 must be 0. A1 is 0. Let's say second one is b1 and third one is also minus b1. You can write minus b1 and b1 also. There is not any problem. Both are same thing. Actually, we are just talking about these two numbers. So how many vectors you can construct which has form of 0, b1 minus b1? You can construct infinite number of vectors. Infinite number of vectors. 0, 1 minus 1, 0, 2 minus 2, 0, 100 minus 100, 0, 100 minus 100, 0, I minus I. All these vectors can be represented by these vectors. And you can assume that all these vectors are just a parallel vector. To avoid the parallelity, we introduce the unit vector. So what we can do, we can treat them as a unit vector if it is normalized. So what I will do, phi 1 must be equal to 1. So from here, I can find b1 is equal to 1 by root 2. So what is my phi 1 vector? The phi 1 vector is 1 by root 2, 0, 1, minus 1. If anybody will write 0 minus 1, 1, that is the same thing. So what we have done, we can get, and yes, this is uniquely defined. This unit vector is uniquely defined. There is no other unit vector. There may be n number of vectors, but all n number of vectors will just a single unit vector because all them are parallel. So what we have get? We have get that basically for lambda is equal to, so you can just get for lambda is equal to minus 1, phi 1 is equal to 1 by root 2, 0, 1, minus 1. This is my first vector. Let us try to calculate the eigenvector corresponds to lambda is equal to 1. Hence, there is 3 cross 3 matrix. So we have to find two different vectors which belongs to eigenvalue lambda is equal to 1, and they have to be orthogonal. They have to be orthogonal. Look at what is going to happen. So we have 1 0 0 0 0 1 0 1 0, and what we have, let's say it has phi 2 is a2 b2 c2, and this must be equal to a2 b2 c2. Now from here you can write a2 is equal to a2 and c2 is equal to b2, or b2 is equal to c2. And you can again find one more vector. something like, you can again find one more vector, something like 1 0 0 0 0 1 0 1 0, and this is, let's say, A3 B3 C3, and this will equal to 1 A3 B3 C3. And again here you have A3 is equal to A3 and C3 is equal to B3 and B3 is equal to C3. So here you can find a phi 2. Let's say phi 2 is A2 is equal to A2. So this I can write A2, and that is B2 and B2. And here also we can find a same form, A3 B3 B3, and let's say this is phi 3. Now look at the real problem. The real problem is that if you will take the scalar product of this vector to this will be 0. A2 into 0, B2 into 1, B2, B2 into minus 1, minus B2, and you can add it, it will get 0. And you can find phi 3 into phi 1 is also 0. The scalar product of phi 3 and phi 1 is 100% 0. So now what is the real challenge? The real challenge is that how many vectors we can construct phi as a phi 2, as a basically form of A2 B2 B2. How many vectors you can find? You can find infinite number of vectors. And in the same form, you have also get A3 B3 B3. That is also same form. But what is the real challenge? The real challenge is that these two vectors must be orthogonal to each other. Normalization we can do it easily, but thing is that this phi 2 and this phi 3, even if they are has the same form, we can construct the orthogonal vector. Let me give you another explanation what we need to do. Now let us try to see the analogy. And I can use different color for this analogy. You can assume, hence these two vectors have same form, exactly same form. A2, B2, B2 means these two number is same, another number can be different. And this number is different, these two are different. What we can claim that these two vectors are in same plane. So let's say they are in same plane. And this phi 1 is all about perpendicular to that plane. So any vectors belongs to this plane will be always perpendicular to phi 1. Hence, these two vectors are degenerate. They are actually in the same plane. And in same plane, how many orthogonal set you can find? Suppose I have chosen this one as my orthogonal set. Then obviously this one is my first set. Then this one is my orthogonal set. I am taking the clockwise rotation. And suppose someone will take this one is as my vector, then another orthogonal vector is something like this one. Someone can take, I can take a different color such that you can understand what I am going to say. Suppose you just want to know this is my one vector, then this must be my another orthogonal vector. So what is the main thing? The main thing is that you can find infinite number of orthogonal set, and you can easily normalize it. So you can find an infinite number of orthogonal set. But this one, you have only this vector, that's it. But for this lambda is equal to 1, you have this vector, then orthogonal vector is this vector. If you have this vector, then orthogonal vector is this vector. If you have this vector, then orthogonal vector is this vector. So what you have to do? You have to either choose this one or you have to choose this one. either these two will make a complete basis, or sorry, these two will make a complete basis, yellow, or you can have either this two will make a complete basis. So it is very tough to identify that from which set we try to calculate all this thing. This is the real challenge. Let's try to find what should be the eigenvector corresponds to lambda is equal to 1. So right now, are you clear? What is the real challenge? If you have any doubt, you can just ask me right now. Okay. So let's try to calculate the phi 2. So what we can do, we can arbitrarily choose one vector with ourselves. So I am choosing the arbitrarily the phi 2 is, I am choosing phi 2 is a2 is equal to 0. So I can choose 0, b2, b2. So phi 2 is 0, b2, b2. And I can find b2 with the with the normalization condition. So phi 2 is equal to 1. So from here b2 is equal to 1 by root 2. So for lambda is equal to minus 1, the phi 2 is equal to 1 by root 2, 0, 1, 1. Now, so what I have done, I have choose one vector arbitrarily, which will belongs to this plane, which have exactly same form. So I have chosen this vector. Now this vector I cannot choose arbitrarily. This vector have to be orthogonal to this. Then we have to use the orthogonal relationship. So what will be orthogonal relationship? We have phi 2, phi 3 must be equal to 0. And then what you can get? You can get as phi 2 as 0, 1, 1. 1 by root 2 will be not used there. So this will be a3, b3, b3 must be equal to 0. So from here, from this particular equation, you can easily find that b3 must be 0 and a3 can be any number. So you have phi 3 must be, you can find that a3 0, 0. And now from the normalization, we can find phi a3. So you can from the normalization find phi 3 is equal to 1. So a3 is equal to 1. So what should be the phi 3? The phi 3 is, if I have chosen phi 2 this, then phi 3 must be, so this is lambda 2, lambda 1, lambda 3, sorry, this is for 1, 1. This phi 3 is equal to 1 by root 2, and this will be 1, 0, 0. So what you can have, you can just make one particular set. Similarly, you can make another set. So
हेलो
you
सर
can, just a minute. Yes.
सर ये फाइव थ्री में 1/√2 क्यों लिखा है? इसका तो
Sorry,
नॉर्मलाइजेशन
root 2 नहीं होगा. Sorry, 1 होगा, 1, 1. Good, thank you. Okay. So phi 3 will be 1, 0, 0. Yes, thank you. Now, what I can do, I can make another set. What will be that set? So if you will again going to calculate for lambda is equal to 1, you will get the unique value. And for another set, I can get lambda is equal to minus 1. Phi 1 is equal to, this must be always 1 by root 2, 0, 1, minus 1. And you will check, you can have another set, and that set I am just writing, I am just giving the solution for lambda 2 is equal to 1, phi 2 is equal to, you can have this sort of eigenvectors. So let's say I have chosen a2 is equal to half. So I have chosen a2 is equal to half, then you have 1 by root 2, and this will be 3 by root 8 and 3 by root 8. You can just do with yourself. And if I have chosen lamp phi 2 is equal to this value, then my phi 3 have to come, and this will be a very interesting one. That will be minus root 3 by 8, and this will be 1 upon root 8. 1 upon root 8. You can just do this exercise with yourself. Otherwise, this can be done into your mathematical physics. So what you can do, you have first set, you have second set, and I am giving you, I invite you that you can get the third set. Here I have just put a2 is equal to half, and then I can get each and everything. You can just go for the another number. Take a2 is equal to 1 by 3. You can get another set. Take a2 is equal to 1 by 4. You can get another set. So what you have, but in every set, what you will get, the non-degenerate value will always same thing. Every set. So please, this is also eigenvector corresponds to 1. 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 But if you are taking this one as an eigenvector, then you cannot take this one as an eigenvector or this one as an eigenvector. Means either this will become your unit vector, ijk type vector, or this will become your unit vector. Either they will form a basis and they will make a complete basis. You can check. These three will make a complete basis. Similarly, these three will make a complete basis. But even if they are belongs to, they are the eigenvectors corresponds to lambda is equal to 1. But you cannot choose these and these as your basis vector. So this is a different space. This is a different space. This is a different basis, obviously, for the same space. So this is the one of the wonderful concept that in the quantum mechanics, you have to always find eigenvectors that will form a complete basis. So why we have to consider one set of eigenvectors. Only calculating the eigenvector, nothing, it will worthless. You have to calculate the set of eigenvectors such that it can make a complete basis. I have given you homework. I think I have given you same type of vectors in last class, isn't it? So you can check, they will make a complete basis, they will also make a complete basis. So this is all about eigenvalues and eigenvectors. So let's go for a next topic, that is commutation. If you have any doubt, you can just ask me. Okay, so let's go for next topic, that is this is the final topic of tools, that is commutators.
Sir, to eigenvector basis eigenvector orthogonal condition must satisfy, na?
Yes. Because I just want to use that vector as a ijk, as a unit vector ijk, isn't it? So why they should be orthonormal in nature. So mainly orthogonal, normalize you can do with any vectors. So this is the most important thing. So let's try to go for basically commutators. So suppose you have two vector, let's say A vector and B vector, if I am writing something like this. And obviously we have done our classical mechanics. So this thing is actually analogically comes from Poisson bracket. Okay, but that is not actually Poisson bracket, but analogically they are something like Poisson bracket. So this can be written as AB minus BA. It is not necessary that they will zero. If this commutator, this AB is equal to BA, so if this value equal to 0, then you can say A and B will commute. We will see how important is this thing. But before that, let's try to go for some property of commutator. It is exactly analogically from the Poisson bracket. So you have A and any function of A will equal to 0. You have A plus B and C. You will take the commutator AC plus BC. And you can have, this is most important thing, A, B, and C. So obviously, here order is very important because AB is equal to not BA. But in classical mechanics, they can be same. So AB, so you can write A, go with C, and you have to write B afterwards. And then you can got B, C, you will get A before this. And yes, similarly, you can go for A, B, C. That will be written as A, B. You can write C, and then you can write AC. You can have B here. And obviously, it will also follow the Jacobi identity. So there is not any problem. So you have commutator of A, B commuting to C, plus you can go B, C commuting to A, and then you can go for C, A commuting to B must be equal to 0. So this all property you know from the Poisson bracket, but here we have to use it. And now here we can also prove that something X and Px operator, the X and Px operator is equal to I H cut. How we can prove? You can easily say, what is the X operator? X operator is defined as it will operate on any function. It will just give psi into that function. So this is definition of X. And this is position operator. So this is position operator. Similarly, we have Px psi x is something minus IH cut del upon del X psi x. So what we have to do, we can find what will be the value of X Px. So we can just use this. So this is the first principle you can just use to get any equivalent operator. So what I will do, I will just write X Px and I will just operate on any function psi x. So this is the way you can find the equivalent operator. Otherwise you can use property also once you know this property. So this is a very interesting property. So you have X Px. So what you can write? You can write X Px psi x minus Px x psi x. And it is not necessary, it is 0. So what is X psi x? So you have, so Px psi x will be x and this will be minus IH cut del upon del X psi x minus Px x psi x will be x psi x. So this is the way the operator operates. So what will happen now for this x, this whole function is a function, so it will operate on this particular thing. So what you will get? You will get minus IH cat x del psi x upon del x minus, now this px will operate on x psi x. So this will be minus IH cat del upon del x psi x. And now here is two function, one is x, another is psi x. So the work of operator is over. Now you can do the mathematics. So how you can write this will be minus IH cat x del psi x upon del x minus, you can just go for it, minus IH cat del x upon x is equal to psi x, and second term is minus IH cat, and that will be x del psi upon del x. So this will be minus minus plus. So this term and this term is cancel, minus minus I. So this will be equivalent to IH cut psi x. So this is equivalent to IH cut psi x. So if you are equating the psi x on both sides, then what you will get? You will get x px is equal to IH cut. So this is very interesting. This value is equal to IH cut. And same thing in a classical mechanics. You remember what will be this value?
1.
1. Exactly. So here, this is equivalent to IH cut. So this is very interesting. So similarly, you can do any problem with the first principle, but obviously first principle will take a lot of time. So why we will use the different type of properties. So let's try to do one or two problem for the property angle such that you can find how we can use all this property of xpx. So similarly, you can find ypy is equal to also IH cut. But if you will find xpy, then obviously that is 0. So it's a very trivial. So, and you have also know, and you know also that this thing x and the position and momentum is not going to measure simultaneously, and there are something to do with the simultaneous measurement and commutators. There are something to do with the simultaneous measurement and commutators. So let us go for first some basically what are the relationship between simultaneous measurement and commutators, and then we will try to go for the problems. So let's try to go for this. This is very important. Look at what we have. Suppose I have a operator A, and A will operate on phi n. We will get an phi n. So what is an? An is the eigenvalue of operator A with eigenvector phi n. And we have another operator. Let's say B is another operator. And what is the story of B? The operator A and B is going to commute. And if A and B is going to commute, so if A and B is going to commute, what we have, AB minus BA is equal to 0. And we can just write, and we can operate phi n on both sides. So I have phi n here minus B A phi n is equal to 0. What will happen? A will operate to phi n. We will get A n phi n. So I can write AB phi n is equal to B an phi n. And an is a number, so you can write number anywhere. So it is not operator, it is a number. So an is eigenvalue, so it is a number. So it is a b phi n is equal to an b phi n. Now what is conclusion? The conclusion is very nice. What I can read? I can read that b phi n is also eigenvector of A with eigenvalue an. Now look at, you can compare these two vectors. We compare these two vectors, and what you can say? You can say A phi n is equal to an phi n, and same time what I have, A b phi n is equal to also an b phi n. So at least from these two equations, I can equate A to an to an, then I can write b phi n. At least I can write not in term of equality, but as a term of proportionality, I can write b phi n is proportional to phi n. It's a very huge statement. What is meaning of proportionality? Meaning of proportionality, that means you can find the parallel vectors. And parallel vectors are always eigenvectors. So you can have eigenvectors. So this phi n can be also eigenvector of B. So you can just write this particular thing. So from here, we can make a conclusion. The conclusion is very nice. And we can just make a statement that if A and B is going to commute, if A and B is going to commute, then A and B can be simultaneous measurable quantity. So it's a very interesting thing. So if you have A and B are going to commute, A and B are going to commute, then what you can get? You can make a conclusion, because B phi n is proportional to phi n, then you can make a conclusion that they can be simultaneously measurable. Means, what is meaning of simultaneously measurable? Means if you have delta A into delta B, it may be equal to 0. There is not any uncertainty into finding that particular thing. So there can be infinite number of uncertainty principle into quantum mechanics. Those vectors who are not going to commute to each other, they will give one set of uncertainty principle. Similarly, as we have calculated that x and px is equal to I h cut, then I have the uncertainty principle between delta x into delta px h cut by 2. Why there is uncertainty principle? Because x and px cannot be simultaneously measurable. But if the any physical quantity or if any operator are simultaneously measurable, means they are going to commute. And if they are going to commute, there is not any uncertainty between them. There is not any uncertainty principle. So uncertainty principle is directly correlated to commutation relation mathematically. So this is one of the beautiful thing of this particular observation. If you have any doubt, you can just ask me. Then we will go for some set of examples. So when somebody will give you two operators and they will ask you that these two can be simultaneously measurable or not, what you will do, you will take the commutation and give the analysis. If they commute, they can simultaneously measurable. If they cannot commute, obviously they cannot measure simultaneously, and there must be some uncertainty principle. So there is n number of infinite number of uncertainty principle. So let's try to go for some basic problem based on commutation and obviously on based on this particular matrices and operators. Okay, so let's try to calculate x square px. So obviously you can use the psi x part and then you can use calculate separately. I am using the property. This is, I can write x into x px. So how you can go for this? You can just write x px. At time I will write x afterward. Then second time again I will write x px, but second time I will write before. Even if they are commuting, I will use this thing. What will be x px is equal to ih cut x, and what will be x px? That will be ih cut. Ih cut is a number, so you can write 2 ih cut x. Similarly, you can have x px square. I am just writing directly. That will come out 2 ih cut px. But these are trivial. In examination, one time they have asked, what will be value of x square px square? This is the real problem I just want to discuss. Now you will write that x square px. One time you will write px here, and second time again you will write x square px here. And what is x square px? Is 2 ih cut x. And what is px? X square px is again 2 ih cut x. And now you can take 2 ih cut and you can write x px plus pxx. You cannot write this thing as 4 ih cut x px or 4 ih cut pxx. So first option was 4 ih cut x px. Second option was 4 ih cut pxx. Third option was this, and fourth is one another. There is not any problem. So obviously you have to always keep in mind the ordering of the operator. So this is very interesting. You have to always keep in mind how you can order the operator. So this type of problem will come into your examination. And order is very important in quantum mechanics. In classical mechanics, you can write this all thing as 4i. Sorry, there is not any I. So that can be, suppose I remove this thing, then you can write 4xpx kind of situation. Now, the last part of all these operators is matrix representation of operators in a basis. So let's try to go for the writing the matrix representation of operator. Suppose I have any operator A and I want to represent in, I want to represent A in matrix form, in basis. So you have to write some basis. In basis, let's say this is phi 1, phi 2 up to phi n. So you have to make n cross n matrix with this basis, and this can be defined by this. So what will be matrix element? So if I want to write the matrix element AMN, what is meaning of that? So if I am writing something like this, meaning of this, there is a vector, so there is an operator, let's say phi n, and then you have phi m, and then you have another number. So I just want to write what will be the operator AMN. So this operator AMN, sorry, this is the matrix element. So this is the matrix element. AMN is given by phi m. So A will be sandwiched between m and n. So phi m, A, phi n. So either you can calculate each and every matrix element, or you can just go for the shortcut. So I am just giving you the shortcut method. So suppose how you will write this particular thing. You can just use, let's say this is A, and suppose I just want to write a matrix in a basis of phi 1, phi 2, phi 3. So I will write phi 1, phi 2, phi 3 as a ket form in a same sequence. In a same sequence, we will write the bra form here. So this will be phi 1, phi 2, phi 3. So what will be this element? This element phi 1, A, phi 1. So this will phi 1, A, phi 1. This number is phi 1, A, phi 2. So this will be phi 1, A, phi 2. And similarly, last one is basically, let's say, as phi 3, phi 1, A, phi 3. So this will be phi 1, A, phi 3. And similarly, you can write each and every number. So you can write this number as phi 2, A, phi 2. These are diagonal. This number is phi 2, A, phi 1. This number is nothing but phi 2, A, phi 3. Similarly, you can write phi 3, A, phi 1, phi 3, A, phi 2, and this is again diagonal phi 3, A, phi 3. So you have to calculate all these number. And yes, you have to define the operator. So once you define the operator, then only you can write any operator in a matrix form. You can represent this same thing in a integration form also. So what will be if I am writing A M N? Suppose A is given as a some functional matrix, then you can write phi M star A phi N dx. So I have to represent A as a function of X. And obviously we will go for minus infinity to plus infinity. So there is not any problem. So this is a matrix element. This is not expectation value. I will talk expectation value when it comes to this particular thing, postulates. Just a matrix element. So let's try to do one problem for the matrix element, and then we can conclude this particular part. So if you have any doubt, you can just ask me. Suppose I define an operator A, which is written as A phi n is equal to n, and it will give you phi n minus 1 or n plus 1. Let's say go for n plus 1. So it is definition. So operate on phi 1 means I will operate on phi 100. What I will get? I will get 100 into phi 101. So this kind of operator is this is defined, and it is also given phi n, phi m is equal to delta nm, means they are orthonormal. What I want, I just want to represent mat A in a matrix form in basis of phi 1, phi 2 and phi 3. I just want to represent 3 cross 3 matrix. It can go to infinite, but for the practical purpose, I just want to represent A in a particular basis. So how we can write? So just do this thing. So let's say this is A. Here I am writing phi 1, then I will writing phi 2, then I will write phi 3. Okay. And here we have phi 1, this is phi 2, this is phi 3. So what will happen? A will operate on phi 1. What you will get? 1 A2. A will operate on phi 1, will give you 1 phi 2. And phi 1 and phi 2 will be orthogonal. So this will be 0. So I am just writing it. This thing is phi 1 A phi 1, which is phi 1. A will operate on phi 1. This will be 1 and phi 2. And 1 can be write anywhere. This is the number you can change. So you can write phi 1, phi 2. So this will be 0, the two orthogonality. So this will be 0. So again, A will operate on phi 2. It will give phi 3. Phi 3 and phi 1 is again 0. A will operate on phi 3. It will give phi 4. Phi 4 and phi 1 is 0. Now A will operate on phi 1. This is phi 2. Phi 2 and phi 2 will be 1. So let's try to calculate this one. This is very interesting. I just want to calculate phi 2 A phi 1. So A will operate on phi 1. You will get A 1 phi 2, and there is phi 2. You can write number anywhere. This is 1 phi 2 phi 2. So this will be 1. This will be basically 1. And again, A will operate on phi 2, it will go to phi 3. Phi 3 and phi 2 is 0. So this is 0. A will operate on phi 3, then this is phi 4. This will be again 0. Again, we will go for A will operate on phi 1. This will go to phi 2. Phi 2 and phi 3 is 0. Again, this is very interesting. A will operate on phi 2. It will give phi 3, but the number is 2. So this will be 2. And then A will operate on phi 3. It will phi 4, phi 4, phi 3 is 0. So what is A operator? A operator is basically 0, 0, 0, 1, 0, 0, 0, 2, 0. This is all the operators. So this is equivalent operator in a matrix form. And yes, and please, this is not an eigenvalue equation. This is just operators. So eigenvalue equation you will get only you have the same function is here. So this is just a definition of operator. It will just operate on phi and it will raise one step above. So you can just construct this type of operators, and we will construct it in the harmonic oscillator, in angular momentum algebra, n number of places. You have to just keep it mind all this particular thing. So
Sir,
if you have any doubt, you can just ask me. Yes.
sir, if we take more phi's, suppose we take phi 1, phi 2, phi 3 up to phi 5, then we get a 5 cross 5 matrix A. Then will
Yes,
the 3
yes,
cross
yes.
3 and the 5 cross 5 matrix will both of them be the same matrix, or we will call
No, no,
that
no,
these two
no,
are
no.
different
They will
matrices?
obviously different matrix. They will different matrix.
So,
It
sir,
okay. It may be that phi 3 is a subspace of phi 5. Are you getting this thing?
sir, I'm
It may
just
be
confused that will the how will
no.
I identify which was my original
It will
base?
just depends that what are the basis vector. That's it.
Okay, sir.
If I will give you 3 basis vector, then it is 3 cross 3 matrix. But in general, it may possible. In general, it may possible that you have n cross n vector, and in this n cross n vector, there are subspace, and that subspace can be different operators.
Okay,
It
sir.
may be possible. Okay, we will discuss it when the this thing will come into picture. Hydrogen atom or angular momentum will come into picture. You will see there may be subspace. Suppose I will go for the matrix for energy, and in the energy operator or in the energy matrix or Hamiltonian matrix, you have subspace of angular momentum operators. Okay, that is different issue. But right now you have to just focus on what are definition and how to apply. What are the actually thing will happen that is much more complicated than this is these all definition. So we have
Okay, sir.
just uh, done the definition part, and this is more than enough for anybody to start the quantum mechanics. But before that, it is very difficult to talk in a quantum mechanical language. So what we have done, we just make the script. We just make a script, nothing else. We just make alphabet, something A, B, C, D, E, F, nothing else. And now, what is our next target? To make a grammar. Because if you will not make a grammar, obviously some grammar is also there, but actual grammar for the quantum mechanics in the name of postulates, such that we can apply and analysis the our quantum mechanical system. And the quantum mechanical system is not a good word. Quantum mechanical observations, we can analyze all these things. So tomorrow and next 3 and 4 day is the most important classes, and everything is related to all these things.
Excuse
Yes.
me, sir.
Hmm.
Sir, please explain how we got two, sir. Two there, sir,
How
in the
you will
map.
get 2?
Yes, sir.
This one.
Ah, yes, sir.
Just write phi 3 a phi 2. Okay. Then a will operate on phi 2. What you will get?
Yes, sir. Phi 3.
Phi 2 to phi 3 from this rule. Okay.
Okay, sir.
And
Okay, sir.
take
Thank you.
2. This is phi 3. Take 2 outside. Phi 3 is 1.
Okay, thank
Okay.
you, sir. Okay, sir.
Okay. Okay. Thank you.
Thank you,
We
sir.
will meet tomorrow, and we will discuss the postulates.